we are back with a new episode of AI Right, and as always, I've got Andy alongside me. Andy, how are you?
Very good, very good. Well, enjoying the rain. Went for a big long walk in the rain there, so that was fun.
I know, it
How are
was
you,
pretty
Kris?
miserable, pretty miserable. Yeah, I'm good, thank you. Just busy Wednesday. Obviously, Easter weekend upon us, although that's afterwards.
I know.
But and yeah, we were supposed to have the privilege of Megan joining us for the first time for a few weeks, but she is poorly, so
Yes.
no co-host today. But
Gutting, gutting. We have totally ruined our gender balance.
we have to be fair. Yeah, obviously brings a lot to the table as well. So our listeners will need to make do with just us two. But we're very lucky to be joined by Paddy McNabb, that we both know well. Paddy, thanks for joining us. How are you?
Excellent to be here. I've been following this podcast for a while now. I always look forward to the link coming up on LinkedIn. So I've been waiting for a couple of years for you to ask me to come on this, Kris. So
You're the
finally,
first person who said
Yeah.
that. You're the first person
He
who
was the
said
first
that.
person. He was the first person to tell me he was privileged for the invite. So I was
privileged,
buzzing
honoured.
off the back.
I think,
Yeah,
I
no,
think, Kris, we've discovered our one listener. It's Paddy.
I know at least 5 people that listen to the
Well,
podcast.
At least 5 people. 4 of them are Paddy.
we can't be accused of not giving back to the community that we're getting the listeners on the show. But no, Paddy, we were chatting last week and you were telling me about RISC and obviously the work that you're doing and a bit of research that you've been doing in this subject. So I floated it past Andy and Megan, thought, yeah, kind of emerging tech, and obviously how it supports kind of scaling generative AI capabilities. So I thought, yeah, really interesting subject to kind of get our teeth into. But yeah, we always kick off by introducing yourself to our listeners. Do you want to give us a bit of background to yourself, Paddy?
I've been working for sort of 20 years in software. I'm actually an electronic engineer by degree. My undergrad and master's was in electronics. But then I spent the bulk of my work, my career in energy systems. A PhD was in energy systems, always with a software edge and a statistical machine learning edge from sort of 2006 onwards. So and in the last sort of 2-3 years, I was into the financial sector. That's where I know Andy from NatWest. Did a bit of work in the public sector as well. Yeah, and I've sort of been on board the AI train for the last few years. Working on GenAI and deploying LLM and agentic solutions.
How have you found the AI train? Are we going to a good destination?
Part hype, part substance, I would say. If you know where to look, there's plenty of value to be found. But if you know yourself, guys, there's a lot of stuff out there. Tooling's coming out thick and fast. New architectures, all that sort of thing. So yeah, you sort of have to be very careful with where you focus your time, because you know it is limited.
Obviously, you've been involved in trying to build and scale customer-facing applications that are driven by LLMs or agentic systems. So part of the conversation today about RISC-V came from troubles of scaling GenAI at enterprise level. Would that be fair to say, or do you want to introduce it slightly different?
That's right, Kris. Yeah, I think we've all been through the experience where you're doing a proof of concept or an MVP, and as soon as you have your connection to your LLM setup, whether it's OpenAI or Vertex or Bedrock or whatever, you build sort of a skeleton solution. You're always amazed that, well, at least superficially, it works, or it's sensible, and it turns values, or it looks to be the kind of fix to your problem. And then once you bring that from sort of proof of concept through MVP, and through all the governance processes you might have in your organization, jumping from dev to test to prod, that's when the real issues start to come out, and you start to realize, well, you were almost not like fooled, but you were really sort of teased in a sense by how well it looked off the bat. And then if your project or your application is successful and users adopt it, that's when you start to look at your token limits and the cost of those tokens as well. And then you start to think, how does this attention mechanism actually work? And why are tokens costing so much money? And why am I using so many tokens? And then once you go deeper and deeper into the fundamentals of it, you sort of realize that, to scale these things post the MVP in production, especially customer-facing applications, from like, say, 25,000 users to 10 million users, you sort of realize that, okay, I've got tools at my disposal where I can limit, tool calls and LLM calls and reduce tokens, but what's happening out there architecturally with the LLMs, what's stuff moving away from full multi-headed attention to gated query attention and different ways of trying to capture those relationships between the tokens and the prompt. So that's what's led me down the route of looking at those types of solutions, and a very natural fit or natural place for those types of efficient solutions to sit are on the edge. And then, okay, what sort of compute frameworks and instruction sets are out there? What's on smartphones? What's on wearables? What's on industrial sensors? We've all heard about GPUs. We've probably heard about tensor processing units, neural processing units. ARM x86 is probably on your laptop, but not a lot of people have heard about RISC-V and what it is. So yeah.
I was just going to say, Paddy, are you looking at edge devices because that's your job, or are you just kind of interested?
Yeah, that's a question. It's certainly not my job. If you look at the if you look at the spectrum of if you look at the spectrum along the dimension of sort of locally deployed, efficient edge AI, local, secure, low latency, all the way up to, say, your big enterprise, agentic application, proprietary API calls to LLMs across the board. I'm closer to that end in the day job. But at nighttime, I switch, I get the cape on and I start.
You're like a kind of AI Batman, right?
I start contributing to more in the embedded AI space and the gaps that are in the RISC-V tool chain, compiler tool chain, compared to the likes of NVIDIA and CUDA, ARM, and things.
We'll come 5 in a minute, but I'm really keen on understanding the psychology here, because I hope you don't mind me probing you on this, Paddy. So what's driving that kind of interest in edge and embedded? Is it because of your engineering background and that sort of the world you came from, or is it just, you just think that's where the next challenges are?
Actually, I was thinking about this recently. I was saying to you at one point, Kris, that the first time I came across the kind of acronym RISC-V was actually, I don't know if you remember, but I am into Rust, or I was into Rust.
I remember. Paddy McNabb. Yes, I remember.
I jumped on another bandwagon, the Rust bandwagon, a few years ago, and one of the key places where Rust has gained adoption is in blockchain, the cryptocurrency. And I did a bit of hobby programming in Rust on blockchain stuff. And I remember everyone's heard of Bitcoin network, but there's the Ethereum network. There's loads of networks, but the Ethereum is probably the second biggest one, and it's got its own Ethereum virtual machine, and that does all the calculations needed to authenticate transactions and secure the blockchain and stuff like that. But it's slow, and blockchain is getting slower because the chain is getting bigger. So the guy that kind of developed the theory off the bat, he's been talking about moving to this thing 5 for a long time. I never understood what that meant or why you would want to do that. And it wasn't until I started looking into 5, and because of it being open source and extensible, the reason why RISC-V is a solution to the Ethereum problem is that people have written custom Ethereum extensions to the RISC-V instruction set. So it's a way for them to take those kind of very specialist mathematical operations that happen on the blockchain and discretizing them and putting them onto the compute. So, but to answer your question, blockchain, LLM inference, stuff like that probably goes back to my background. Like, we did a lot of digital design in university and register analysis. I think in general, when you do in school, if you do like mathematics, GCSEs or A levels or higher, you're always doing it in the continuous time frame, integration, differentiation, but you never actually think or taught to think, how would you take that equation or that system and put it into a discretized domain like a computer and shuffle bits about to make that filter work. So I really enjoy thinking in that kind of register way and thinking in matrices and vectors and bits shifting and stuff like that. I think that's it fundamentally.
Yeah, if we've got any educationalists listening, you've heard it here. We should have space and time on the lower high school syllabus. I love it.
Exactly.
Very good. Finite elements in first year. I love it. Let's do it. Well, we're gonna have to ask Kris. I don't know if we have any other lead up questions, but we're gonna have to ask, what is RISC-V? Please tell us, Paddy. Please tell the listeners.
I don't know. No. Yeah. So
that'd be a bombshell.
No, RISC-V Well, RISC is it's reduced instruction set computer. That's what it stands for. And the instruction bit's really, really important. So what does a computer do? So you hear people talk about, oh, I compiled my application down to a binary or machine code. And that literally is just a massive chain of binary ones and zeros. But when a computer sees that, it needs to think, how do I chop that up? And what do the chunks of bits mean? And what should I do when I see a 100 followed by a 0000? And like ARM and like x86, RISC-V is the instruction set. It's a recipe book that tells the computer, once you see the first 8 bits, that's the opcode, that's add, subtract, divide. The next 5 bits are the registers. Where's the data I'm going to operate on? And then the next sort of, what's that? The next 19 bits will be something else. Write your result to here, or use some lower level flavor of that opcode, and that's it. And you can imagine from the very basic level there, within RISC-V, there's a must-have base instruction set. And that's just it's your 32-bit integer or your 64-bit integer, and that's got all your very low-level simple operations in it. That has to come with 32 registers. Each register is 32 bits, and that's really it. Data's in the registers. There's instructions in instruction memory. RISC-V tells it these codes mean something, and that's it. So, you can build a CPU just from that standard. That's
Okay.
RISC-V. Yeah.
You saying that's it as if it's nothing, right? I'm looking at the wiki pages just now trying to understand, and I'm like, this is over my head. Do you feel happier in this? Do you feel happy in this space because again of your sort of your engineering background and the stuff you studied, or is this stuff you've picked up just through time? Because looking at instruction sets and all of that stuff sounds a bit deep, if you like. Yeah.
I must admit these questions are very good but very probing.
I'm trying to understand because I'm like, this is not our usual bread and butter on the show, right? Just to your point before about, the modern sort of, like you say, in enterprises, basically a lot of kind of use cases, most use cases are just LLMs as a commodity, etc. You're sort of talking about how do you optimize at the lowest level, and there's tons of work going on in this space, but we've not had anyone on the show yet who's kind of in the weeds. So that's kind of interesting. But yeah, but it's just like, so RISC-V is this instruction set, it's reduced instruction set. Has the instruction set been optimized or is it a more general thing?
That's sort of where it is now. So if you look at what I guess from my background, having I know you studied physics at an undergrad PhD, and I don't know about you. I had a few pints. During my 4 years at Edinburgh Uni and after that PhD levels. I don't know how much went in. There is this sort of strange thing. I don't know if it's just me or it's a general thing. We all probably cram for our exams and our finals and all that, but there is this lingering sense. Once you know something, you can't unknow it. And even though if you haven't touched it for, say, 20 years, there's still this sort of latent, under the bonnet sort of wish to do something. And I think that's where this has come from. There's always, I sort of know a bit about how it works under the bonnet, but I want to know more. But I guess where RISC-V is going. So I talked about the base integer set. That is the must-have thing for RISC-V. You have to have that. You have to have your 32 registers. But apart from that, where do you go next? There's all sorts of other extensions. There's a math extension, atomic extension, various other ones. But the really big one for AI in the RISC-V sense is the vector extension. So look at any sort of LLM inference and the amount of matrix multiplications that have to go on once the prompt comes in, and those tokens are embedded, and then those embeddings are multiplied across all these query, value, and key matrices. You fill up your KV cache until you're finished, and then you start your decoding and then predict the next token. So huge amount of matrix multiplication going on there. Really what that is dot products. So it's you're building out, multiplying a vector by a vector, storing that, moving on to the next one, storing that. So you're never going to multiply an entire matrix multiplication given the size of them in modern LLMs. So that matrix is broken down into tiles, and you compute the tiles, and you move on to the next tile until that matrix multiplication is finished. I put out a blog last week on Quinn 2.5 0.5 billion parameter model, 169 matrix multiplications for one token going through the bot. That's just for the next token. Next token, do it again.
Yeah.
So a huge amount of that going on, but really it's dot products under the bonnet. Now that's where the vector extension was useful, because that allowed RISC-V to define a vector register. Same thing, 32 registers, but they're much wider. So you can put a larger chunk of that matrix, or the 2 bits of that matrix, into the vector register. You can multiply them in one instruction. So instead of a scalar operation where you're looping and looping one value, one instruction, stick them into massive vectors, do one vector wide operation in one clock cycle, accumulate that result, and then move on to the next thing. So that's where RISC-V is at the minute. But then if you look at something like ARM, which is the Advanced RISC Machine, is what ARM stands for. So you can already see that was born out of a RISC-1 from in 1980. So they've got matrix extensions now. So again, instead of just storing the vectors in a vector register, they're now looking at a matrix tile register, where you can take a tile of the matrix and represent that in an efficient way in the memory, and then multiply them. The next step from that would be your tensor extension. So looking at not just the matrix tile, but at another dimension of almost tiles stacked on each other, which is what a tensor is. So that's what RISC-V is the minute. It's but the key thing is, a key thing about RISC-V is that it's not licensed. It's not beholden to roadmaps like ARM is. x86 is Intel. They don't license their IP out of Intel really. ARM is just an IP licensing company. They license their blueprints out. You pay them a one-off fee plus a percentage per chip shipped. RISC is no licensing. You can extend it any way you want. You can build custom instructions, all that kind of thing to fit your LLM. So very different.
And just so that we bring everybody along the journey, including me, what is the relation?
Number one in that list.
Yeah, what's the relationship between the physical chip and instruction set, and then, like you said, extensions? How are they linked? Because you're seeing things now, and this is where my head's kind of going, just prefacing the next couple of questions. I've just seen something about people burning onto chips the architectures of LLMs directly. Yes,
that's right.
So, I'm trying to map, if we're trying to map the landscape for people, how does, someone builds a physical chip in a lithography lab, somewhere in Taiwan. What's the relationship between that physical hardware, the instruction set? Does that come later, or is that baked into the actual sort of the transistors and stuff on it? And then when you say extension, is that just a change that happens after the physical artifact created, or does it have to be incorporated? You know what I mean? Can you map that out for us? Map that out for us. Yeah.
No, so that's it. If you come to build a chip and you're building a silicon and you're burning them on the transistor circuits on that silicon across different lanes, so you have integer and lane and vector lanes and matrix lanes and all that sort of thing, they have their own transistor circuits in place to deal with that sort of operation that is integer or vector or whatever. If you take a RISC-V, if you say I'm going down the RISC-V route and I'm going to use the vector extension, but I'm going to build a matrix extension instruction on top of that, that is tied to the design of your chip. You have to include the transistor circuitry to manage that matrix specification or that vector specification or that integer specification. And then when you add those RISC-V instructions, which are really just opcodes. So as I said before, if I see a matrix coming in, another matrix, I'll say, right, I want a matrix to matrix multiplier operation.
Yeah.
Okay, that gets compiled to this opcode. This opcode comes in, the CPU decodes that and says, right, I know that's a matrix operation, and I know where in the silicon that has to go to make that happen. Oh, I also know where the matrix registers sit to put the data in for all that transistor circuitry to do the operation, and then that gets spat back out on the chip into memory. The issue with the Talus one, which you mentioned, which I'm still getting my head around, was Talus have actually if we say we're going to import a weight, LN weight from memory, and we're going to get that onto the chip or into the register, then that's sort of encoded in a transistor circuit as a weight, and then the output of that will get put into some sort of multiplication operation with the activation value coming in. So there is that loading time of the weight from cache and the activation from cache as well. Whereas what tablets have done, they've burnt the model architecture into the transistor circuit, so you weren't constrained by memory load. You're constrained by how quickly the electrical signal passes through that silicon, because that's your answer. That's your answer at the end of it. So how quickly the transistor gates can switch on and switch off and do all those operations. You're talking RISC-V optimized. Well, there's a class of model out now called Liquid AI, LFM2, and they benchmark their 1.2 billion small LFM on Snapdragon, which is ARM, and they're getting about, I think, 100, 150 tokens per second. That Thales one was for Llama 8 billion was 17,000 tokens per second. They were getting
it's crazy.
But it's inflexible. Like once you burn the LM onto it, you can't.
There's no import, or keras.load new model. But so just so we get that mapping right. So what you're saying is, so there's chips of transistors laid on them in a certain way. They can do certain operations. Is there RISC-V chips, or is it there's a set of chips that are compatible with RISC-V but other instruction sets, or what's the mapping? How does that work?
It's a chip compatible with RISC-V, and that'll be it. Yeah. The other thing as well is that it isn't just the circuitry. It's you need to set the width of the vector registers as well in bits. So if you have 32 vector registers, you might say, right, my chip supports 265 bits per register.
Gotcha. Right.
You're tied
so
to
there's some spec about how the actual stuff is burned. You say that's RISC-V compliant. When you do an extension, is it just an extension to the instruction set, but it's all compatible? So you're not changing the chip, or do you have to change the chip? If you see what I mean.
So yeah, it's a former. So if somebody's come along and say, right, this AI thing's blowing up and I want to have this, a chip manufacturer says, I think Llama 8 billion's great. I'm going to build a chip where we can efficiently deploy that. And all the smartphones are going to buy it and stick it in there, because AI and the AIs are going to buy that. Once you do that with, say, if you make a decision in your architecture, okay, I want to use ARM for that, then you have to take what ARM have. So ARM's mature, and they've got vector and matrix extensions and all those sorts of baggage that you may not need. You've got to take the whole lot. You've got to pay a license for it. With RISC-V, what the key thing you can do with RISC-V is say, right, I want to use the LLM. It's got a special convolutional layer. So it's only got like 6 query attention layers and like 10 convolutional layers. And they're much quicker and much more CPU friendly than the multi-headed attention stuff.
Yeah.
How can I build the compute to manage that convolutional calculation, because that doesn't exist? You can't use ARM, because if you go to ARM, you'll say, we haven't got that. Okay, we'll put it on our roadmap. We've got to do a gap analysis, and in 2 years' time, here you go. Whereas RISC-V, you can build it into your chip. So you can put the circuitry onto your chip. You can write the RISC-V instructions for it. You've deviated from the current RISC-V standard, but that's fine. That's what it's for. You deploy that. You release a chip, release the instruction set. The other thing, which is no free lunch, you also have to update certain compiler tool chains, because it has to know that instruction exists. So if I say it's Llama 8 billion and it's got a convolutional layer, something has to link that convolutional bit of the code in PyTorch or whatever to the RISC-V convolutional instruction that you've built onto your chip and linked through the RISC-V instruction. But, companies can do that in 3 months and have a chip out that's got this really cool ability now.
Really?
And that's
3 months.
And
3 months. That's amazing.
And then you can sync that. So then all you have to do is to just be part of the RISC-V ratification standard meetings, and you can then sync your brilliant new design in with the RISC-V standard, because the market has spoken and said, we like that. So get it into the standard. So it's different to how ARM would work, where you have to sort of prove that this is going to be good. Just build it, deploy it, and then go, that's good or it's not good. So that's how it works. So I got a board, a Milk 5 board at the minute. It's a SpaceMit chip on it, and hidden in there is a custom matrix, custom matrix extension. And SpaceMit have gone out and built that into the chip, built the instruction set. So I could take any LLM, compile it down, as long as the toolchain knows the matrix extensions there, compile it, and then use all those wonderfully new efficient matrix instructions on RISC-V. So yeah, that's how it works.
See if I can bring you back. So obviously we first get into the conversation because we're chatting about scaling generative AI for enterprise or for just general purpose products. What we were chatting about previously was that obviously we're seeing the amount of compute that's required for that, and there's a huge investment into data centres absolutely everywhere in order to handle that. But what you were saying to me was there's so much more compute required on smartphone devices or general purpose devices and on IoT wearables that this is the infrastructure required can sit on RISC-V rather than data centres or on specific like NVIDIA GPUs, stuff like that. Is that where the biggest need for something like this is?
I think so, Chris. Yeah, I would also say that the compute's one thing. So the compute is just that layer you need to do the number crunching. The other thing is that, take what are quite common GenAI use cases now. You've got stuff like complaints management and routing, text to SQL, and a number of other things under the conversational AI chatbot umbrella. But a lot of those things, you take like a 4.1 or a 5 or a Gemini or whatever, like they're, I don't know, 20 trillion tokens trained on the internet. If you almost picture a multi-dimensional space of knowledge, they have it. But we're only using it for this wee tiny, text to SQL. It's just its ability to convert English language or whatever language into SQL. So you're paying for all this massive compute and all the latency and all of that, but you really want that thing. So what people may do, they may say, well, let's just take the model, pre-trained model, and fine tune it and stick a layer on top of it, or do that, least order rank adoption or whatever, or parameter efficient fine tuning, and then, steer those weights closer to our use case. But, you still have all the other weights there and you're going to pay for that, whatever. But, so I think there is an aspect. I'm a firm believer that the future is sort of task specific in AI. Stuff that's just good at sort of one thing instead of being great at other stuff. And and that in theory should make models more specialized and smaller. I think you would do it anyway, regardless of the compute platform you want to stick it on, whether it's GPU, NPU, RISC-V or whatever. But then when you start looking at the wearables market and the industrial sensor stuff that needs to always be on, even though it may not be activated, then you sort of need low power stuff. And that's where RISC-V comes in. It's got that base modular set, it's got optional extras, and that's it. You can really cut down the baggage of stuff that will eat up your power. So it's getting that instruction density per milliwatt of power is what it's all about. So if you can get sort of task-specific stuff on the efficient compute, you're great. The one thing I would say is that the people that are really good at that compute bit don't necessarily know much about the benchmarking in the kind of task-specific sense. They'll look at throughput and tokens per second and all of that. They may even look at some of the wider sort of benchmarks you may see in OpenAI reports and all that. But the bit that's always sort of missing is, if I quantize the weights down or I make all these efficiency savings, is my SQL still as good? Or is whatever my use case is. So I think that bit's missing.
I think that's such a good point. I've even seen this in kind of different settings already. We've fallen into the trap sometimes of, I think you even mentioned this at the top of the call, Paddy. It's like, I've integrated all this. It's spitting something back. It's working.
That's great.
Whereas when you do real evals and stuff, you're like, oh, actually, it's technically working in the sense it's answering prompts, but to your point, it's not answering the question very effectively, or it's not giving me SQL that runs or finds the right data, or it's hallucinating sort of syntax and the code it's generating and stuff like that. So
yeah,
I think that's such a good point. So you've got RISC-V. This is helping us kind of have a bit more open, extensible ecosystem, allowing us to optimize where we need to optimize. We mentioned IoT and edge. Are there any killer use cases you've seen just to this point about use cases where you think that sort of AI at the edge capability is really, really powerful? I can think of a few from kind of jobs I'd done before. But I was wondering what you were thinking. You know, is there a few use cases you're like, oh, that is really cool. That is where AI at the edge will change things.
Yeah, so I think one of the good areas that I come from, I've done a lot of work on industrial sensors in previous jobs. The main part of my career was working in phaser measurement units with General Electric, and very compact format, but you're still sending the data from an edge location to a centralized repository so people can look at it. And then all the AI bits centralized, like, I'll get the data in, then we'll do all our great, AI and machine learning on it. But I see a big use case in sticking some of that stuff in the edge. Don't even send me the raw data. Do that analysis there and then. Time series or condition monitoring. Is my wind turbine about to break down, kind of thing? Do that in the edge and send me a summary signal to say I'm good or I'm not good. Again, harsh environments stuff, low power, all that comes into play, and depending on how competitive that sector is, how quick to market, can you get stuff out the door, capture market share, all that. So I think with RISC-V, there is the low power extensibility aspect of it, but I do think there's a market share aspect to it as well, where you can you can build things and iterate things quicker, get them out the door,
Yeah,
get
so
them embedded.
your time to market's a lot smaller. No, I was thinking similar things because of what we did at Agreco about we were trying to push stuff to the edge more. To your point, it was the exact same setup. Is there much talking about it using it in space and stuff? There must be, because I feel like space, because it's low power, like you said, it must be a great idea if we're going to send out probes or kind of Curiosity rover and stuff. Imagine that having an LLM on it.
It's a good point. You made me think of something there. My dissertation, at Edinburgh Uni, your dissertation was a thesis, but you had to do 6 presentations in a group leading up to it. And I was terrified because I'd never done a presentation before. And I was like, I had sleepless nights for weeks beforehand. It was the lead digital lecturer was the guy leading this. And the topic was memory systems in harsh environments. And it was like space and high radiation.
Yeah.
So we had to go with a fine-tooth comb, go through magnetic storage, SRAM, DRAM, solid state in your laptop. RAM was one of the ones at the time that Motorola were building. There was one that used this sort of graphic memory, which never took off. And there's all these memories. But I remember stuff in that about, a cosmic ray can just knock the charge out of your charge coupled device and the whole thing will just, just breaks down.
Well, they say that with airplanes, right? Yeah. They say that with airplanes, you get bit flipping with cosmic rays, exactly.
Yeah.
Muons coming in.
So it's whatever they were put into space, a harsh environment. But again, go back to low power, extensibility. There's tons of other stuff in RISC-V I've not covered. Like you can build out of your vector registers. You can make logical vector registers. In theory, they could be 19,000 bits. Imagine a multiplication 19,000 bits by 19,000 bits. You can build these massive registers and stuff. It's really, really flexible. But if anybody wanted to get involved in it, there's a huge opportunity for contributing to the gaps in the tool chain. It is less mature than other architectures, but that's the fun bit. I hate using the word low-hanging fruit, but there is lots of stuff to do.
No, you've said it now.
CPP, low-level virtual machine, tensor vector machine, IRI, all these compilers. Lots of stuff needs to be done to bring RISC-V up to speed.
Well, if you've got links and stuff, we'll definitely share it after. You've convinced me. I never thought I was going to be a chip person. I've always operated a higher level of abstraction, but now you've sold it. I think this is super exciting, super interesting. So I'm going to go away and learn more about instruction sets, about chip architectures, about RISC-V, and see if I can contribute to the toolchain. That sounds awesome.
You can get this in. You can buy a Banana Pi or Jupyter, all RISC-V development boards. You can buy them. Plug them into your laptop, and you can start building, start compiling, start messing around with the instruction sets and the intrinsics and see what breaks.
Love it.